Here we are in a new unit talking about simplifying radical expressions. And when we say radical expressions, we're talking about things that have a radical. You might recognize it as the square root symbol. Things that have a square root symbol that not necessarily a square root, but maybe a cube root, maybe a fourth root. We're trying to simplify expressions that involve these things. First, if we want to identify the square roots of real numbers, what we're looking for when we say identify the square roots, we're looking for a number, find the number x so that x times x equals 25. That's what I say, that's what I want to find when I'm trying to find the square root of 25. So what number times itself equals 25? Since 5 times 5 equals 25, then 5 is a square root of 25. What if we consider negative 5 times negative 5? That also equals 25. So negative 5 is a square root of 25. Let's try and use that same idea. So this would be 5 or negative 5. What number times itself equals 49? 7 or negative 7. What number times itself equals 0? That'd be 0 or negative 0, which is just 0. What number times itself equals negative 9? You may intuitively think, what about negative 3? But those two multiply to positive 9, and so since they don't multiply to negative 9, they are not a square root of negative 9. For this course, what we're going to say is that does not exist. That is not in the real numbers. It says identify the square roots of the real numbers, and we're trying to find a real number answer for this course. So our square roots of negative 9 do not exist. You can do this on the calculator. So on your calculator, you have a second button on the top left. This is the TI-30 XIIS calculator, our course calculator. TI-30 XIIS. That's our calculator. You've got the blue second button, and then down below, you'll see this x squared button, and just above it in blue is a square root button. That's what you want. You want that square root. Any blue button, you have to hit second to get the blue button. So what we're going to type in is second, then hit that x squared button. It'll give you the square root symbol and a parentheses. You type in 36. You close your parentheses. That closing parentheses is right here. You hit equal, and it's going to tell you that the answer is 6. You could do the same thing for 4 over 9. What you type is second square root. It's going to open a parentheses. You're going to type 4/9. You're going to hit equals. It's going to give you a decimal. Remember, to get a decimal to a fraction, the easy way is there's a F-D button here. You hit second F-D, hit enter again, and it's going to change it into a nice fraction, 2 over 3. And since this one gives us decimal, we'll leave a decimal in the answer. So we want second square root 0.04, and we get 0.2. The square root button is on the calculator. That's where I would start with any problem, is with that square root button, and see if it simplifies it for you. If not, we'll go and have to do it by hand. All right, type these in your calculator and see what you get. The first one, you should get a domain error. For the same reason that we said the square root of negative 9 doesn't exist, we're going to say this does not exist for this class. We're not interested in finding a square root of a negative number. That would take us out of our real number system. The second one, though, when we type negative square root 144, we get negative 12. Notice the difference is where the negative is. This one right here does not exist. The negative was inside the square root. It doesn't exist. But this one is negative 1 over 3. Because the negative was outside, we can actually get an answer. These, again, you can type in your calculator to get the answers. All right. There's another button on your calculator. So the first one, easy to type in, square root of 4, 2. The square root button is the one that we've been using. It's second x squared. Now, for a cube root, a fifth root, a fourth root, a sixth root, for roots other than a standard square root, what you're going to have to do is use this button here. It's the x root button, and it's just above the caret symbol. You hit second, hit the caret symbol, and it'll give you an x root. Now, we want the index. We want this index to come first. So this, for example, the way that I would type this in, I want a third root. I would type in 3 because I want a third root. Then I would type the little star root button, the X root button. 3x root, it opens a parentheses automatically. 64. Then hit enter. You should get 4. Try this as many times as you need to until you get the correct answer. The same thing with the second one, the fifth root of negative 32. The way I'm typing that in is I'm typing 5 first because it's a fifth root. 5 is the index. 5 x root negative 32 should give you negative 2. Fourth root of 81, 3. Sixth root of 1,000,000, 10. You should be checking these in your calculator. The square root of negative 100 doesn't exist. The fourth root of negative 16 does not exist. These are all values we can get with the calculator. All right, evaluating specifically the nth root of a to the n. Specifically, the n and the n have to match. You see that? The root and the power match. If n is a positive odd number, then we just get a out. We just get the number that was inside the square root. If n is a positive even integer, though, then we get the absolute value of a. Not just a, but the absolute value of a. If these two numbers match and they're odd, we just get a out. If they're even, if n and n are even in the same value, then we get the absolute value of a out. That's very important. This is going to come into play especially when you're solving quadratic equations and things like that. So here are some examples of that. The rules are still at the top. That's the same exact two rules. The fourth root of negative 3 to the 4. This would be our a value, right? N and n, they're the same, and they are even. And so I know I need to get the absolute value of negative 3, which is just 3. Here, since n and n are odd, they're the same but odd, 5 and 5. They're odd. That means I need to get just a out, which is negative 3. Even, they match. You know that with no index, it's an understood index of 2. We get to the absolute value, x plus 2. Odd indices and odd exponents, we just get a plus b. This one's a little bit tricky because the index and the exponent don't match. But we can rewrite this as the square root of y squared squared. That's the same thing as y to the fourth, y squared to the second power. Now our index and our exponent match, and so we should get out of here absolute value y squared. Here are a few for you to try. Following the same idea as the very last one, y to the 8th is the same thing as y to the 4th squared. And so now that the index and the exponent match, and they're even, we get absolute value of y to the 4th. On B, 27 is 3 to the 3rd, a to the 3rd. We're doing whatever we can to get the index to match the exponents, whatever we have to do. And since that's an odd index and odd exponents, we just get the a values out here. All right, odd index, odd exponents, they all match, and so I'm just going to get a over b as my answer. Take a second, try and rewrite this one. This is a toughie. 81 is 3 to the 4th. We've already got x to the 4th, it matches. For the y's, y squared to the 4th is y to the 8th. 2 to the 4th is 16. And now the 4th power and 4th roots will all go away, but I do have to keep the negative, and I do have to keep an absolute value sign around the whole thing because it's even exponents. All right, the Pythagorean theorem is one way that we can exploit these squares and square roots. The Pythagorean theorem says as long as we have a right triangle, then the two legs square to equal the hypotenuse squared. So that's saying a squared plus b squared, since they're both legs, they're on the sides of the right angle. A squared plus b squared equals c squared, the hypotenuse. The hypotenuse is always the one away from the right angle, on the opposite side of the right angle. So a squared plus b squared equals c squared. That's our Pythagorean theorem. Trying to apply that. If I have 5, I don't know what this is, so let's call it x. These are on the right and left sides. Those are going to be my a and b. What's really important, it doesn't matter which one's a and which one's b, but it really does matter that this one over here is C. So when I write out my Pythagorean theorem, I can say 5 squared plus x squared equals 13 squared. I can try and use my calculator a little here. 25 plus x squared equals 169. Subtract the 25 and get x squared equals 144. What number squared equals 144? This is just like we were doing at the beginning, the very first slide. What number squared equals 144? Well, it could be 12 or it could be negative 12. But since I'm talking about a triangle here, a physical object, a triangle, I'm not going to keep a negative 12. I'm just going to say x must be 12. The missing side must be 12 units long. Here, 12 feet long. All right, a couple of new rules here. If you ever have a fractional exponent, we're going to start down here. If you have a fractional exponent, that's the same thing as writing it as a root. Notice this looks like a to the m, and we have an a to the m here. The power stays as a power. The denominator of that fraction becomes the index of the root. So a to the m over n becomes the nth root of a to the m. This is something you just have to memorize. Another thing you just have to memorize is if you have a negative power, x to the negative n, same thing as 1 over x to the n. It puts it in the opposite part of the fraction. So for example, x to the negative 5, same thing as 1 over x to the 5. X to the negative 12, same thing as 1 over x to the 12. 1 over x to the negative 7, same thing as x to the 7, right? A negative exponent just puts it in the opposite part of the fraction, numerator versus denominator. Let's see if we can take these things and apply them. So first, negative 8 to the 1 over 3. That's the same thing, using this rule right here as the third root of negative 8 to the 1. That's the same thing as the third root of negative 8. Negative 8 to the 1 is just negative 8. And in the calculator, the third root of negative 8 is negative 2. All right, 81 to the 1/4. That's the same thing as the fourth root of 81 to the 1. That's the same thing as the fourth root of 81. And the fourth root of 81 in the calculator is 3. We'll try another. Negative 100 to the 1/2 is the same thing as the square root of negative 100 to the 1. That's the same thing as the square root of negative 100, which does not exist. Oh, I'm sorry. I did this totally wrong. That's actually the answer to the next one. Notice here's a difference, and I'm glad that we noticed this, is that for this question here, for this question C, the negative is not necessarily being, the 1/2 exponent is not necessarily being applied to the negative. Here, the 1/2 exponent is absolutely necessarily being applied to everything in the parentheses. On this example, the 1/2 exponent is only being applied to the 100. The negative's just following along. So this is the same thing as negative square root of 100 to the 1. Same thing as negative square root of 100. Same thing as negative 10. I'm glad I caught that before we went on. It does matter. The parentheses absolutely matter here. And if you were to go back and type these in your calculator, actually, if I had copied that calculator, that little up arrow, the caret, is how you do an exponent. This is how you do an exponent. And so on this, what I would be typing in to check it is I would be typing in, for example, parentheses, negative 100, caret 1/2. I would hit enter, and it would tell me that that's a domain error. All right, 16 to the negative 1/2. That's the same thing as 16, square root of 16 to the negative 1. And remember that negative exponent rule here? That's the same thing as the square root of 1 over 16, which is equal to 1 over 4. Here's a few more for you to try. 8 to the 2/3. That should be the same thing as the third root of 8 squared, which simplifies to the third root of 64, which is just 4. 100 to the 5 over 2 is the square root of 100 to the 5. And this is how that simplifies. 1 over 25 to the 3 over 2. You know 2 is going to be the index of your root, so it's a regular square root of 1/25 to the third power. 4 to the negative 3/2. That's the same thing as the square root of 4 to the negative 3. 4 to the negative 3 is 1 over 4 to the 3. And 4 to the 3 is 64. And the square root of 1 over 64 is 1 over 8. Same on this last one. Negative 81 to the 3 over 4 is the same thing as the fourth root of negative 81 to the third, the fourth root of negative 531, 441, and the fourth root of a negative in your calculator gives you an error, so that does not exist. We're almost to the end of this slideshow. Convert each to radical notation. This is just saying, because there's no numbers here, we want to convert it to radical notation. A to the 3/5 is the same thing as the fifth root of a to the third. 5 to the 1/3 is the same thing as the third root of 5 to the 1 times the third root of x to the 2. Since they both have the same index, we can combine them and make them the third root of 5x squared. The next one, 3y to the 1/4, notice that 1/4 power is only applied to the y. So that's the same thing as the 3 times the fourth root of y. Same thing here, that negative 3/4 power is only applied to the z, so it's the same thing as 9 times the fourth root of z to the negative 3. The z to the negative 3, because of that negative exponent rule, same thing as 1 over z to the 3. Last slide here. Convert each expression. We're trying to go backwards from a radical to an exponent. So this first is the same thing as b to the 3/4. b to the 3/4. I should write that a little better. b to the 3/4. The second one is the same thing as 7a. The whole thing is in a square root, so 7a to the 1/2. The entire thing to the 1/2. Notice the difference in the next one. Only the a is in a square root, so it's 7 times a to the 1/2. The 7a altogether is not to the 1/2 here. Only the a is to the 1/2 power. In the next lesson, we're going to be looking at simplifying things with exponents as well, and combining things, combining radicals using exponent rules, combining expressions using exponent rules.